Hi, everyone. Thanks again for attending. Today I'm going to talk about absolute standards for the measurement of gloss. And that's why we're all here. Just a little more about me. I have been at NIST since about 2009, and I've been working on a variety of projects in color and appearance and also in remote sensing. But what I wanted to bring up is prior to joining NIST, I was the optical engineer at Hunter Lab in Virginia. And that's the company that Richard Hunter started after he left NIST. And I was there for about 14 years. And there I designed instruments for measuring color and appearance and gloss. But at the time, gloss, when I was there, gloss was not part of our suite of instruments that we sold. It is now, I understand. But while I was there, I was primarily working on spectrophotometers and colorimeters. So here's the outline of my talk. Let me get my pointer here. So first, I'm going to give a brief summary of the methods to calculate gloss and for the calibration of gloss reference standards. Throughout, I'm going to be referring to two papers, and they are those of Wolfgang Buda of the NRC, and I apologize if I have the pronunciation wrong, and Maria Nadal and Ambler Thompson of NIST. The citations for these papers are given here, and I highly recommend you obtain a copy if you're interested in learning more about accurately measuring gloss. Along the way, I will briefly take a look at black glass as a gloss standard and also a wedge configuration that Gail showed earlier in the case of transparent standards. Next, I will focus on showing how gloss is calculated from the specular spectroreflectance, where the Fresnel equations play a significant role. And then I'll show that the calculations for gloss follow the equations given in the two references. I'll then talk about a gloss scale from a variety made from a variety of optical glass types. And these glass types are readily available, and I hope to implement such a scale at NIST very soon. I'll also show how the scale can be expanded using a simple anti-reflection coating so that a wider gloss range for each of the three angles of incidence can be generated. The scale would be useful as a means to check, say, for systematic measurement errors and to actually calibrate a measuring instrument. So we know the standard geometries for the measurement of gloss are the 20, 60, and 85 degree angle of incidence. By definition, from ISO 2813 and ASTM D523, the gloss value equal to 100 is obtained for any artifact or a standard whose refractive index at the sodium D line of 589.3 nanometers is equal to 1.567. This refractive index is usually associated with a black crown glass, such as Carrara black, but in reality, the index at the D line for this black glass is typically not equal to 1.567, but closer to, say, 1.53. But considering for the moment the case of the documentary standard at each of the three angles of incidence, it would be given by the Fresnel equation shown here at the center, where I'm assuming the incident light is unpolarized. We need the specular reflection to calculate gloss. In this equation, theta is the angle of incidence in air, and theta prime is the arc sine of the ratio of sine theta divided by the refractive index. So following the definition and following Buda, if n sub d is 1.567, then this table shows the value of spectral reflectance, and it's denoted by rho. That's calculated using the Fresnel equation. By definition, each of these correspond to a gloss equal to 100 units. And the ratio of the gloss divided by rho is shown in the last column, which If you have a copy of Buddha, you will see that that is equation 3 in his paper. Now, if n sub d does not equal to 1.567, then the gloss is 100 times rho of the sample at the d line for each of the 3 angles, divided by rho of the documentary standard at each of the 3 angles. Note this is a monochromatic calculation made at 589 nanometers. As an example, suppose the refractive index was actually 1.527, a number that is usually associated with black glass. In this case, the gloss at the 3 angles of incidence would be 89.2, 93.6, and 99.4. So if you were using this black glass as your standard and you were measuring at 60 degrees, you would adjust your meter to read 93.6. But in practical gloss meters and in the specifications of both ISO 2813 and D523, the gloss is actually measured over a spectral range corresponding to the CIE 1931Y observer function, and also for polychromatic illumination corresponding to standard illuminance C, as Gail mentioned. So there is some ambiguity, particularly in the calibration of practical reference standards, because a monochromatic setup is not used. Buddha addresses this and shows how the accuracy can be improved. He presents the equation for gloss as a product of 3 terms. The first term we've already seen, and it arises from the documentary standard. The second is the ratio of the monochromatic reflectance of the primary standard at the D line to its polychromatic reflectance indicated by the letter pi here. And the third is the polychromatic reflectance of the sample being measured. The polychromatic reflectance is defined here in the blue box, and it's the integral of the illumination times the observer times the spectral reflectance divided by the integral of the illumination times the observer. And remember that the illumination is defined in the standards to be CIE illuminance C, and the observer is defined to be the 1931 photopic observer function Y. So Nadal and Thompson rearranged this equation a bit and presents the gloss calculation in the form of a measurement equation with an associated uncertainty. Here, the gloss of a test sample that I'm just calling G sub T is 100 times the ratio of the monochromatic reflectance of the primary standard and the documentary standard, multiplied by the ratio of the luminous fluxes of the test sample and the primary standard. The luminous flux is defined at the right here, and it's a quantity that can be measured. So given the measurement equation, an uncertainty in gloss can be directly calculated from an estimate in the uncertainty in the components using the law for the propagation of uncertainty, which I'm referencing here. In practical instruments that, today, you might be using a spectrometer as the detector instead of just a photocell. And in that case, the integration would be replaced by a summation over the spectral range. From this point on, I'm going to be using this Nadal equation for the gloss. So here are the key points to take away from the 2 papers in the previous slides. First is that the Fresnel equation is used to determine the spectral reflection and then the gloss. The documentary standard has an N sub D of 1.527. The black glass has been traditionally used as a gloss standard, but if its refractive index at 589 nanometers is 1.527, then the gloss would be about 89, 94, and 99.4 at 20, 60, and 85 degrees, based on the monochromatic calculation, and not 100 at each angle. If the index is actually not 1.527, but you adjusted your meter anyway to read, say, 93.6 for 60 degrees, then you would be building in an error. So to eliminate that error requires knowledge of either the actual refractive index of the black glass or the actual spectral reflectance of the black glass, or a calibrated value for the gloss, and then your meter could be properly adjusted. Furthermore, the ISO and the ASTM standards define gloss in terms of monochromatic radiation at 589 nanometers. But because the instruments that measure gloss use polychromatic illumination, and because that's also specified in the standards, then an error results. And Buddha shows that the error can be up to about 0.5%. It's not too bad as far as a measurement instrument is concerned, but this level of accuracy is not desirable if you are a National Metrologic Institute and you want to provide a gloss standard with a calibrated value. So to reduce the error and to provide the highest accuracy, the luminous reflectance should be used instead. So this requires knowledge of the specular reflectance of the test sample or the standard to which the sample is compared. Before continuing, here's a few black glass standards that are available for purchase. They can take many forms, probably a shape matched to the measuring port of the associated instrument. On the left here, an example of a black glass available from aerospace metrology and electromechanical calibration in the UK. This looks to me to be a square of about 100 by 100 millimeters. That would be a size consistent with the Lucidian ceramic color tiles that many people, including NIST, use as color calibration standards. At the center, Konica Minolta offers a black glass with their Nova Gloss Flex 60 instrument. I think these have a magnetic base so they can attach to the instrument when not being used so that they're not lost. That's a great idea. On the right here, Elcometer in the United States provides a black glass with their Model 480 instrument. And I give the links to the web pages here so you can learn more about them, if you like. So what are the desirable features for any gloss standard? Well, first, if it's transparent, it should take the shape of a wedge so that the reflection from the back surface does not reach the detector. It must also be long enough so that when it is tilted with respect to the illuminating light beam, that the illuminated area is completely contained. And this is especially critical at 85-degree angle of incidence, where the illuminated spot can grow by about a factor of 11.5. The exact shape of the wedge depends on the instrument design and even the sample holder, but about a 6-degree wedge is good enough to isolate the first surface of the reflection. The standard should be homogeneous so that the refractive index over the length of the illuminated area is the same. It should be hard so it doesn't scratch easily, durable so that it doesn't wear, and easy to clean. It should also be readily available so that it can be easily reproduced and to keep costs to a minimum. And it should have dispersion characteristics similar to any test sample so that errors are minimized when taking the ratio of the luminous fluxes. You don't want to take ratios if the reflectance of your test sample and your standard don't have the same general spectral shape. So otherwise, if there's a wavelength calibration difference between your gloss instrument and the instrument that calibrated the standard, there could be an associated error in the ratio. Carrera black glass has been in use for many years at NIST and the NRC, but it does have some disadvantages. First, its refractive index at the D line is about 1.527. That's fairly far from the documentary standard of 1.567. And we have seen that this should result in a gloss equal to about 94 at a 60-degree angle of incidence and not 100. The NRC has shown this black glass can be chemically contaminated over a few years, resulting in a gloss change of up to about 2%, but that's recoverable by repolishing. Also, NRC show the refractive index is not uniform, with a variation of up to about 0.5%. And then furthermore, the surface of the black glass is easily damaged. In this calculation, Buddha works with the dispersion for the average crown glass, which represents the dispersion of black glass, but the actual material composing the glass is not actually known, so the dispersion is difficult to calculate in the event that you don't actually know its reflectance, or the reflectance can't be measured. So alternatives have been investigated, and Buddha showed that fused silica is an option, but its refractive index at the D line is about 1.458, resulting in gloss equal to about 71, 82, and 98 at the three angles of incidence. These are far from the documentary standard values of 100 and could be a problem if it's used as a reference and the instrument is nonlinear. So instead, it would be best to find an alternate material closer to the documentary standard, which Nadal and Thompson found, and that material is the BAK50 optical glass. So this is a plot of the normalized refractive index for the BAK50, the black glass, and the quartz, and this plot was taken from Nadal and Thompson. This is all normalized to the refractive index of each of the materials at 560 nanometers. And you can see that the dispersion of the BAK50 is, basically overlays that of the black glass, which is the historical standard. And, and having the similar dispersion means there would be no issues or potential errors arising from spectral features, as I mentioned before. But the quartz isn't quite the same, but it's not bad, and it still can be used. So here's a plot of the dispersion curve for BAK50 at 22 degrees C and 1 atmosphere over 380 to 780 nanometers, or equivalently 0.38 to 0.78 microns. So this curve was generated using the Optic Studio optical design software program. You may know it as Emacs, and I use it for a lot of things. But one of the things it has, it contains a glass catalog, and from it, you can generate dispersion curves just about for any glass that's contained in the catalog in the software. So BAK50 is one of the catalog glasses that is in the software, and zooming in at 0.589 micron wavelength, Zmax is giving a refractive index as 1.5676653. So, we want to compare that to 1.567, which is the documentary standard. Obviously, it's almost identical, and we'll see how the calculated gloss of this compares to the gloss of the documentary standard in a few slides. But first, so we have a catalog value for the index, but does the actual refractive index agree with the catalog values? So Nadal and Thompson thought about this, and they took a look at a few different wavelengths where they measured the refractive index using the minimum deviation method. As you can see, the agreement is actually quite good, with the root sum square of the differences equal to about 285 parts per million. So the catalog and the measured values agree pretty well. But I would say ultimately, for the best accuracy and for your peace of mind, that the spectral reflectance, instead of an assumed refractive index, can be measured if you have the ability to do that. And at NIST, we have an instrument that we call ROSI that does have that ability. And I give a link to this if you want to learn more about it, if you desire. Of course, an instrument like that could also measure the spectral reflectance of a black glass too. So if you have an ability to use something like this, it would be very, very good. Okay, moving back. So here's the predicted reflectance for the BAK50 at 589 nanometers. That's a function of the angle of incidence of the light incident from air. And this is according, again, to Zmax. From this, you can see why the gloss varies and increases as the angle of incidence increases, because the intensity of the reflection increases. So note that the incident unpolarized light splits into S and P polarizations, and they are plotted separately here in the blue and the green. At 60-degree AOI, the reflected light is almost entirely S-polarized since it's near the Brewster angle. The average of the S and P polarizations, here I plot it red in the graph, that's used to calculate the gloss. And here at the top left, I give a link to discuss, that discusses polarization if you're interested. So here are the plots of the spectral reflectance of the BAK50, plotted from 380 to 780 nanometers for the three angles of incidence. And now I'm only showing the average of the S&P polarizations. So these plots illustrate, that a software program like Zemax, or of course the Fresnel equation itself, can be used to calculate the spectral reflectance for any optical glass, if the dispersion is known. So let's take a look at calculating the gloss of the sample now using the BAK50 as the standard, and then developing a gloss scale. So I'll be using, again, the Nadal equation for gloss. The first step involves the use of the Fresnel equation, though, to compute the spectral reflectance of the documentary standard and for the BAK50 standard at the three angles of incidence and at 589 nanometers. So for clarity, I'm breaking the calculation into two terms. Term one is the sine squared contribution, and term two is the tangent squared contribution. As you can see, the resulting spectral reflectance for the two standards are almost identical, with the ratios after multiplying by 100 equal to about 100.18, 100.11, and 100.01 at the three angles of incidence. So the worst case is at 20 degrees, and that's only off by about 0.2% from the documentary standard. So the next step would be to compute the luminous reflectance for a test sample. Consider Heraeus Supercell 311. This is a synthetic fused silica glass that NRC has used in the past and might still be using. And we also use it as a test sample. So on the left here is a plot of the catalog dispersion curve for the Supercell 311 that is obtained from Zemax. And on the right is the computed spectral reflectance at the three angles of incidence. So obviously these curves are available in tabular form, which we can use. So the next thing to do is to compute the spectral reflectance of the BAK50 standard, and that was already shown in a previous slide. I think it was 13. So what you want to do is form the product of the illuminant S times the reflectance rho times V lambda, which is the 1931Y photopic observer function. You want to do that over 380 to 780 nanometers and then integrate. And finally, you want to multiply by the BAK50 factors on the previous slide, appropriate for the angles of incidence. And the result shown in the table, where I'm using GV instead of GU, sorry about that, that refers to the computed gloss value for the Supercell 311. So here's the calculated gloss for the Supercell 311 for any angle of incidence, and not just for the three standard geometries. So you can see that the gloss approaches 100 as the angle of incidence increases. And also note that the sensitivity in the gloss value to the angle of incidence can be determined directly by taking the derivative of this curve. And the sensitivity looks to be about a maximum at about 85 degrees for this particular gloss sample. At 60 degrees, the sensitivity is about 0.66 gloss units per degree. So if you know the angle of incidence, say to only a couple tenths of a degree, then you can expect an error of about a tenth of a unit of gloss for this sample. And also, the sensitivity is dependent on the gloss value itself. So the uncertainty component associated with the angle of incidence is a function of the gloss value, which is important if you want to calibrate it. So to form a gloss scale, I'm going to repeat the exercise for a variety of optical glass types. To reduce the cost, choose only readily available optical glass types and limit those to what are called preferred types, as designated in vendor catalogs. So what is preferred? Preferred implies that the glass is frequently melted and readily available and presumably less expensive. Here's a list of some of these glass types. It includes calcium fluoride, the Supersil 311 I mentioned already, and BK7, which is the workhorse optical glass from which many lenses are fabricated. And then there are two higher index dense flint glasses, NSF5 and NSF6. By the way, the letter N is a shot designation for glass types that are environmentally friendly, meaning they contain little or no lead or arsenic. Zmax and the methods that I talk about here calculate the value of glosses shown here in the table for each of the three standard geometries. And note that they span values below and above 100, which is nice. And that's useful for checking linearity. But also note there's a relatively large gap underneath, let's call it under calcium fluoride, the gloss for calcium fluoride. It may not be important if you're measuring strictly specular samples, but it's very important if samples having a diffuse component are being measured. And in those cases, some of the reflected light is diverted away from the detector because it's scattered away from the receiver. So that would lower the measured gloss value. So it would be very helpful to fill in the gloss scale with values much less than those associated with the specular. So to achieve this, since there are two surfaces to a transparent wedge of glass, why not deposit a simple single layer anti-reflection coating on one surface? For example, consider a quarter wave optical thickness, some people call that a quat, of magnesium fluoride on one surface. Magnesium fluoride is widely used in the coating industry, and given this simple coating deposited on one side of the wedge, Zmax computes the reflectance, and from that, the corresponding gloss, which you see here. You can see at 20 degrees, the minimum gloss is now about 4.4 units for the SF6 glass. And, if you have a scale like this, you can definitely check for systematic errors or your instrument linearity. Or you can also, directly calibrate over these gloss ranges. If catalog values for dispersion aren't trusted, say, from your optical design program, then, you should measure the actual reflectance instead. So just a quick word on diffuse standards. Some show a mix of specular and diffuse, and in this case, the reported gloss would be a function of the amount of light scattered into the solid angle of the receiver, and also a function of the field stop in the receiver, as a scale shown earlier. There are dimensions for the field stop given in ASTM D523 and also in ISO 2813. But I think the measurement is very tricky and perhaps not well defined in the various standards. So I think to really get a handle on the diffuse scatter, the effect of the diffuse scatter on the gloss, I think it's best to start with measuring the BRDF of any potential diffuse component standard, and measure it over a range of view angles a little larger than that expected for the gloss instrument that you're using. And from the BRDF, it's possible to calculate the gloss given the instrument geometry, and thus you could populate the gloss scale with more members. So here's my summary. We've looked at the importance of the Fresnel equation and introduced gloss as a function of the spectral reflectance. Buddha and Nadal and Thompson give detailed overviews and the methods to calculate gloss. Although black glass has been used historically. Nadal and Thompson proposed a more robust gloss standard made from optical glass BAK50, which is stable over time, it's durable, and it's very easy to clean. It has a worst case gloss value of only about 0.2% different than that of the documentary standard. And we're using it today at NIST. A gloss scale can be formed from this glass type and other preferred glass types, some of which I've shown earlier. This would be very useful, not only for calibration purposes, but also to test for systematic errors, in an instrument. A wedge geometry should be used to isolate only the first surface reflection, and one side of the wedge can be coated with a simple AR coating to reduce the specular component of the reflection. And finally, optical design software programs such as Zemax or your favorite program can be used to predict gloss and to help you form a gloss scale. Here are some useful references and some pages that I just pulled at random off the web. There are scholarly articles and many e-magazine articles and knowledge-based information offered by gloss meter vendors that you can find by just performing a Google search. And these, I'm showing just a few. That's really all I had. Thank you.